Fantastic. So right here, we're on the concentrations. And so one of the ways you can think about percentages is if you remember the percents, they were typically gram over gram or weight over weight percentages. That would be called parts per hundred. Okay. These are going to be called parts per million and parts per billion. You've probably heard of parts per million, parts per billion. If not your blood tests, then you've heard it on like pollution reports. Like there's so much lead in the water, typically measured in parts per billion. Okay. Now, these parts per billion, parts per million, they're extremely convenient when you need to talk about very dilute solutions. For example, the amount of lead in water is actually very, very small. Okay. But you don't need a lot of lead in water to actually affect a developing fetus or to affect even your brain chemistry. Lead is actually pretty toxic to you. Okay. So when we talk about these numbers, none of you probably wants to put a 0.00000001. And that would be a real pain to put in tables, right? Or to put out in news reports, because it'd be very long numbers, wouldn't it? And so what we do is we put 10 parts per billion. Okay. So if you think of, for example, a penny would be a part per million of 10,000. Okay, so $10,000, 1 part per million would be a penny. In terms of volume, about 5 drops of food coloring in a bathtub of water would represent a part per million. Just barely visible tinge, right? Okay. And so it'd be a very dilute solution, very, very small amounts. And that would be about 1 drop of food coloring in an Olympic-sized swimming pool would be a part per billion sort of concentrations. Okay. And if you think about that, remember a part per billion is going to be 1,000 times less concentrated than a part per million, right? Because that's the difference between a billion and a million. So parts per million is sometimes referred to as micrograms per liter, because this is just a very convenient ways of doing this. Another way of thinking about that is that would be micro, 1,000, right? And then liter is 1,000 times larger than a milliliter, isn't it? So we've done 1,000 times lower, 1,000 times larger to give us overall a million. Okay. And parts per billion would be microgram per liter. In fact, if you haven't seen parts per million, parts per billion for your blood testing, these are probably the units you did see. Okay. They're actually the same thing. Same numbers. They just put the different way of representing those units. Right. Very common. You'll see that quite a bit actually in your lives that you may just have never realized it. Yeah. You've ignored it because you didn't know what it was. Now you know what it was, so you can see it, okay? All right, so remember that when we do this, this is going to be a percent mass over volume measurement. And so we'll have a percent mass over V would be a parts per 100. The parts per million would just be times 1 million instead of 100 here, okay? And if we were to do parts per billion, you'd be multiplying by a billion instead. So they're actually the same sort of formula for all of those. A percent is just parts per 100 because you multiply by 100, right? Million, multiply by million, so it's parts per million, okay? And then billion, multiply by billion, parts per billion. Okay. So you do the same formula for all those. Okay, so let's talk a bit about dilutions. One way to prepare solutions for lower concentrations is actually to take a solution of a higher concentration and dilute it by adding more solvent. Most of you have already done this to one degree or another. Have you guys ever taken concentrate, or have you guys used the soda fountains? That's probably an easier one. Or those dial-up soda ones where you can pick what flavor it is, and that makes it right there. The Coca-Cola machines. Okay. So that's actually what you're doing when you're using a soda fountain. You're taking a concentrated syrup and then you're diluting it with the solvent, which is going to be soda water, or another way of saying that is carbonated water, right? And so you've done dilutions. You've done probably thousands of dilutions in your lifetime, right? But you may never have realized it. Okay. Now, when you add concentrated flavor in drinks as drops of water, the amount of flavoring does not change, even though you have a lot more solution present. The amount of flavoring in one squirt was originally equal to the amount of flavoring in the water after you've mixed it. And so what you're going to see here is that when we put the more concentrated solution, we're going to dissolve it in the overall amount. That means the solute that you originally delivered does not change even though the volume changes, does it? Still the same amount of solute, okay? Or in this case, flavoring, right, which is the solute. So the amount of solute stays the same because we can either create or destroy mass, right? On the other hand, the volume of the solution can increase by adding the solvent, right? And so the more solvent we have, the larger the volume. And what you'll see is your concentration decreases as you add more and more volume. Another way of thinking about this is all of these numbers had the solute on top, right? And then the bottom was always some sort of volume or amount of solvent, right? Or total solution, okay? And so if you increase the number on the bottom, the overall number gets smaller, doesn't it? Right. So this right here is actually the formula for dilution. It actually works for any dilution. All you need to do here is understand that the units on both sides have to be the same, right? If we put grams on one side, we can't put milligrams on the other, right? Okay. So C initial times V initial equals C final times V final. And this right here is the concentration. This can again be in percent concentration. This could be parts per millions. These could be moles. It doesn't matter. Okay. So molarity, parts per million, or percent concentrations, doesn't matter. The only thing that matters is the C initial and C final have to be in the same units. Okay. If they're different units, then this will not work because the units won't cancel, right? All right, so V initial right here and V final, again, this could be any type of volume. For example, you could put milliliter on both sides, liter on both sides, doesn't matter, does it? The reason for that is because the units will be the same on both sides, right? And so when you divide over, they'll always cancel, won't they? Okay, that formula clear? Fantastic. Really simple formula, really nice one to know, makes life really easy. Okay. You can figure out lots of stuff in the world around you with that formula. All right, so let's talk a bit more about dilution again. The dilution equation, again, works with any concentration unit. Remember that whenever you have these, you have to have the same amounts of solution. It's the denominator in those volume units because you're going to be putting volumes in here, right? Okay. Okay, so the dilution equation, number one, you have to, this is the same problem-solving technique for everything, by the way, if you're actually paying attention to these. What you'll notice is, number one is always establish what information you have, right? Where am I? What do I have right now? Okay. Number two is you always arrange, set yourself up so you can clearly demonstrate what you then need, right? So you're then going to demonstrate what you need. And then finally, you solve for the unknown quantity. So these are some different dilution factors and some concentrated stock solutions we're going to talk about. So the use of a dilution factor is going to be modifying the equation for the dilution equation. Typically, it's going to be used a lot in microbiology and medicine. And this is where they do dilutions repeatedly, the same dilution over and over and over. And they don't want to have to write out the entire equation every time. Okay, so what they do is they just give dilution factors, and then you can take whatever you want to make, what you have, and then multiply by the factor. Okay, it's just a shortcut to that equation. All right. So again, the actual concentrations don't actually need to be known, only how much you want to dilute it. Okay. So you don't actually have to know exactly what the concentrations are in this case, only how much you need to dilute it by. Okay. This right here is your dilution factor. You'll notice that it's just the concentration of the concentration. That's what the dilution factor is. And that equals the volume final over the volume initial. Okay? It's just a rearrangement of this equation here, isn't it? So let's go ahead and talk about a dilution factor here. So let's say you want to make some soup. Okay? And so what you have here is the soup concentrate comes in a can, right? You open the can up, and the directions say add 1 can of the concentrate, add 1 can of water, right? That's a dilution factor, isn't it? Okay. So you have 1 can of the soup concentrate. That's your volume initial, isn't it? Okay. And then you take and add another can of water, don't you? That's 2 cans for the prepared soup volume, isn't it? And so your dilution factor is a 2-to-1 factor. That's all that is. I told you guys you've done this before. Everybody made soup before? Hopefully everybody has. If not, go make some soup after this. All right. So when large volumes of solution are needed, laboratories oftentimes are going to store solutions as a concentrated stock solution. You'll notice that we actually do this a lot too, though we have bottles already prepared for most of the standard solutions we make. Okay. So for example, in the previous example, we have the concentrated soup. This is a 2-time stock solution. So you take your stock solution, and then you would just mix it up with an equal volume of the solvent. Okay. So if you use concentrated stock solution, it's common practice. It's very common for storage of medicines. It's very common for pharmacies where they have to mix up batches, oftentimes where it's not the exact same concentration they want for every batch. So they have different dilution factors depending on the patient. And so then they would give different patients different dosing by using different dilution factors, right? Okay. And so this is your dilution factors. Does everybody go with that so far? All right, let's talk a bit about osmosis and diffusion. So osmosis, our bodies are mostly water. These are composed of a set of specialized aqueous solutions that are going to be, for example, our blood serum. And then we have, for example, the solution inside of our cells. These are slightly different. We also have the environment around our brain cells, which again is slightly different, and our environment in our kidneys, okay? And so we have a series of aqueous solutions that compose the environments of our body. Now, these solutions are going to be found both inside and outside of cells. In fact, even within cells, we can have specialized solution environments. For example, anybody ever heard of a mitochondria? Powerhouse of the cell? Well, acid battery of the cell. So in the mitochondria, there's actually an environment that's actually super acidic compared to all the other parts of your body. That's actually how they generate power, how they generate their ATP. So these solutions are going to be separated by our semi-permeable cell membranes, and semi-permeable meaning that allows some stuff through, but some stuff it does not allow through. Okay? And that's why it can have its own specialized environment. So this again is going to allow some molecules to pass through, but some molecules cannot pass through. Typically, the molecules that can pass through are going to be small and neutral. Molecules that cannot pass through are going to be large or charged. Okay? So under normal physiological conditions, these are going to be isotonic solutions for most of your body. That means that the concentrations of dissolved solutes are the same on both sides of your membrane. If they're not isotonic, then what's going to happen is water is actually going to move to one side preferentially. Okay? And that's what happens when we have osmosis. That's actually the pressure that the water exerts when it's trying to move towards the higher concentration environment. Okay? Has anybody ever put out like salt or put out the salt you scatter on the sidewalks? And you see like it starts sucking moisture into it and dissolving despite the fact that it doesn't have any water around it? Yeah, that's actually osmosis occurring. So that salt is higher concentration than the surroundings, which is in that case the air, right? And it starts absorbing moisture into it until it becomes isotonic. You can also see this if you ever take has anybody ever taken the like sausage bags? The stuff they stuff sausage with and played with it at all? That's not a thing anymore, is it? Okay. Fair enough. Has anybody ever heard of reverse osmosis? Yeah. So reverse osmosis, they take and remove water from a high concentration saline solution, right? Which is usually the ocean. Okay. And so that's reversing this process. Okay, so when a person drinks large quantities of water, it's actually going to dilute the blood. And so the concentrations of your solutes in your body's internal solutions in the blood will actually go down. And this can actually cause some cramping and various different little issues. Normally, it's not a big deal because you have plenty of salt in your diet. But sometimes if you sweat too much, haven't replaced your salts, and you just drink pure water, you're going to cause problems. This is why Gatorade and stuff like that has been developed. Okay? And so, concentration of your salts goes down in your blood. This is going to result in an imbalance between the concentrations of the solution outside of the cell, i.e., they have less dissolved solute in the outside environment of the cell. The concentration inside the cell is then going to have more dissolved solute. And so, this situation is what's referred to as hypotonic. So the solution outside of the cells will be hypotonic, meaning it has less hypo concentration tonic. Okay? All right. So water will then travel through your cell membrane, and what's going to happen is it's going to travel through an attempt to equalize the concentrations of your solutes on both sides. And so that passage, water is allowed to move through the semipermeable membrane because it is neutral in a small molecule. And this pressure of that moving through that semipermeable membrane, that is referred to as osmosis. Okay? That's the driving force here. And it literally is a pressure, by the way. If you were to actually stop the water's movement and try to hold that back, you would experience pressure, force. Okay? All right. So if too much water enters, the cells swell up and they could even burst. And this is called a phenomenon called lysing. In this case of blood cells, it would be called hemolysis. Okay? Literally breaking apart blood cells. This is actually what happens if you were to take like distilled water and you had a huge concentration imbalance. You could actually cause some hemolysis, just a little. It would fix itself pretty quickly unless you mainlined an IV into somebody and put a bunch of distilled water in them. Okay? So it's fairly rare, but you will see it. It's possible to see. So again, as water flows through your semipermeable membrane during osmosis, the water molecules are going to move to the more concentrated solution. They're going to exert pressure on that membrane. And again, that's the osmotic pressure. That's actually the force of it exerting that pressure and moving towards the more concentrated solution. So the more concentrated the solution is that's moving towards, the greater the osmotic pressure. And I'm not joking, if you took a column for this, separated by a semipermeable membrane, you can actually see the water levels actually change. Okay? And they can resist gravity and actually push one side up. Right? This can actually be a surprising amount of force. So, pure water actually has an osmotic pressure of 0 because it doesn't have any concentration to drive water to join it. Applying pressure in the opposite to osmotic pressure can actually stop osmosis. And in fact, you can reverse the process if you apply enough pressure. So for example, reverse osmosis, you literally just apply pressure across the semipermeable membrane. And what you'll see is that water will actually go through and leave behind the salt. Okay? And you end up with an extremely concentrated salt solution, which you typically dump back into the ocean and take the water to drink it or whatever you want to do, depending on what you need. More often than not, reverse osmosis is actually used so as to get very, very pure water. Okay. Uh, More often than not for things like chip factories, that sort of stuff. Purposes that need very pure water for production. So the concentration of dissolved ions in salt water is about 3 times that of blood. So if you drink salt water, what actually happens? Do you get any water from it? Let's say you're on a raft, dehydrated, you're gonna die. What do? Do you drink the salt water? No, you don't drink the salt water, right? Why don't we drink the salt water? Exactly. Because osmosis is in the direction of the salt water, right? Because it's 3 times the concentration in your blood. So it's actually going to absorb water from you. Yeah. And then hopefully you'll throw it up so you don't continue doing that. Okay? But yeah, you can't actually extract any water from the salt water. Okay? If a person were to drink, of course, seawater, that concentration of the seawater is higher than the blood, and so that is a hypertonic solution. Hyper meaning greater, tonic meaning concentration, right? And so hypertonic solution. During dehydration, the cells will actually shrivel up. This is actually a process called crenation. So that's what the cells in your stomach do, and that's one of the reasons you throw up, is because the salt water actually causes your cells to shrivel up, and that's crenation. Okay, so here's your examples. So this is an isotonic solution, and this is a normal red blood cell. Everybody comfortable with that? Okay. And see, it looks like platelets, right? And that's why they're called platelets. Okay. So we see our beautiful platelet right there. It's going to run around in our body and carry oxygen and a few other things. Okay. It's doing great. If we were to do a hypotonic solution, meaning a lower concentration solution, then what's going to happen is your red blood cells are going to puff up and blow up like little water balloons. Okay. What happens if you overfill a water balloon? Pop. Yep. And also, when it's filled up, it's usually more fragile, right? And so these do have a tendency to collide with your cell walls and stuff like that, collide with your veins, and pop. And so that's hemolysis, right? Okay. Now, this is actually very unusual to actually happen, even if you drink distilled water, because typically people have enough salt concentrations in their blood that they can absorb a fairly decent amount of distilled water. Okay. And they'll have maybe some hemolysis in their surrounding tissues of their stomach, but not enough to really cause a lot of problems. However, you can actually see this a bit if you spend too much time in a bathtub. That's actually what you're seeing with your wrinklies, right? You spend too much time in the bathtub, its environment is hypotonic, and so your skin cells actually start swelling up, don't they? Okay, this right here is going to be hypertonic solution. This is if you drink like seawater, right? And so what's going to happen, this is crenation. Your blood cells are going to shrivel and they're going to be pushed in by the surrounding water. Okay? As it tries to, as it's leaving, this is going to empty this of water. And so it has less inside of its support and it shrivels, right? Now, what do you notice about this? It's a little spiky looking, isn't it? Yeah, that doesn't look like it would flow nicely, does it? No, and so you actually get buildups. And so, for example, a lot of people that are sick will go into the doctor and they'll be dehydrated. That's a pretty chronic problem for people that are sick because they don't feel good, they don't drink and eat properly, they get dehydrated. Okay. So, if you go into the doctor when you're dehydrated, they can actually look at your heart, and actually, about 1 in 10 times, they're going to see little buildups in your heart then. And that's actually crenated blood cells. And they clear fairly quickly. They can cause heart attacks and strokes if it's a long-term problem. And that's one of the problems of staying dehydrated for a long period of time. But this actually will then cause them to misdiagnose your heart. So if you ever get a diagnosis on your heart, always get a second look at it if they saw a problem, and make sure you're hydrated properly. Like, it's very, very common issue. Actually just happened to my mother a year ago. Complete misdiagnosis for 3 months almost because of this. Yeah. And I couldn't fucking believe that they didn't know this basic fact and retest it when she was better hydrated. I just couldn't even imagine that was an issue that they wouldn't think of. Anyways, now you all know. Hopefully, you can make sure that doesn't happen to you. So during osmosis, again, water's going to flow through the cell membrane. It's going to flow from an area where the solution is less concentrated to a higher concentration. And so right here, we have water flow from this lower concentration to the higher concentration, of course. Does anybody have any questions about this so far? So again, it flows from the more dilute solution to the less dilute or more concentrated solution. Okay, so intravenous solutions that are delivered in the patient's bloodstream should be isotonic, okay? Or have a very small amount of extra salt solution if you're trying to give them salts. But they should not be significantly hypo or hypertonic, right? You need to keep it very, very similar concentrations as their blood. So isotonic solutions are going to minimize osmosis. Common isotonic IV solutions in hospitals are going to be things like 0.90% mass over volume NaCl. This is your normal saline solution, or NS. And this is usually used as more of like a drug delivery system. Okay? It's just a base to put something else with it, right? And that just makes sure you're more or less isotonic with the blood. Okay? This is another one. This is 5% mass over volume D-glucose or dextrose solution. Hey there. Thank you very much. And this is going to be referred to as D5W for the dextrose 5% in water. Oh, no, you're good. No, you're exactly. I'm sorry, I didn't even know that was there. And so these right here are physiological solutions. They're very similar to what you see in a patient's blood system. Okay. This one specifically to give somebody sugars if they're low on sugars for their brain. Okay. This one over here to give the patient NaCl. Most patients, especially in the United States of America, do not need sodium chloride, but it's a cheap and easy way to get isotonic. Okay. If they have had a super busy day out under the sun, this is not a bad solution to give them. Those are a few other solutions that are usually a little better, more suited for purpose. Okay, but this is a very basic isotonic solution. So instead of using the concentration of molarity, physiological solutions are often expressed in osmolarity, literally so that they can have an osmotic pressure amount. Because you want to ultimately give somebody something that's osmotically the same pressure. Okay? So you don't have an overall flow of water, right? Okay. And so the molarity, which is going to be then times the particles in your solution, because this number here actually is derived from the number of particles in solution. So for example, we were talking before about our NaCl solution here. That has 2 particles in solution because it's going to break up when it goes in solution. Okay? So for every NaCl in solution, there's actually 2 particles. This dextrose solution, every dextrose in solution is just 1 particle in solution. It doesn't break up. Okay? That one stays together. And that's where remember strong electrolytes versus non-electrolytes? That's where that comes into play. Okay, so again, that's the number of particles in solution times that concentration. Blood plasma actually has an osmolarity of 0.3 osmoles per liter. And so that would be the osmolarity of your blood plasma. And that's what you want to keep isotonic to, is your blood plasma. Anybody know what blood plasma is? Yes, so that's going to be your blood without the red blood cells, right? Okay. It's the stuff around the red blood cells. Okay, so if we add a drop of food coloring and we put it into a large beaker of water, the green dye molecules, there's solute, are going to mix with your water, the solvent. This is going to result in a solution that has a uniform light green tinge to it. This process right here is what's referred to as diffusion. Okay? You've all experienced diffusion many, many times in your lives, of course. If somebody was to, God forbid, fart in this room, what would happen? It would spread throughout the room, right? That is also diffusion. Okay? So since spreading throughout the air, that's again a solution. It's diffusing throughout the solution to be an equal concentration throughout. Okay? Now, if we have two solutions, they're going to spontaneously mix, and your green solute molecules are going to fuse into your water. This is going to form one dilute solution that's going to have a final coloring that's intermediate between these two and has a more or less even concentration across the entire solution. Once it's fully diffused, it will have an even concentration throughout the entire solution. Okay. However, a process of diffusion can take a while. Right. Our entire atmosphere is in a constant process of diffusion. Okay. That's actually why weather happens. It's literally trying to do diffusion. It's just taken a while. Okay. Kidney dialysis, this is going to be diffusion, is going to be the movement of molecules in a direction that equalizes concentration. Dialysis is kind of going to be a reverse of this. Okay? So we're going to build up concentration in one area. So what's going to happen is kidneys are then going to act to remove small waste molecules through the blood, from the blood. It's going to do this through diffusion across the membranes in the kidney. Cells and larger molecules are going to reabsorb into the bloodstream. Small molecules will diffuse out of the blood. They'll end up as higher concentration, where they'll move into the urine, lower concentration, and this is the process of dialysis. So what we're going to do is we're going to continuously provide low concentration solution that's going to let molecules diffuse into it. And then what we're going to do is we're going to remove that solution once it builds up too much concentration. And that's going to be urination in the case of your kidneys, right? Okay. In a dialysis machine, you'll literally cycle pure water, right? Okay. Okay. And so a person whose kidneys are failing can actually undergo artificial dialysis. It's going to be called hemodialysis. This is used to cleanse the blood. The reason they have to do it is your waste molecules are going to build up in your blood if your kidneys are not functioning properly. Okay? And so in the process, blood is going to be removed from the patient. It'll pass through one side of a semi-permeable membrane. On the other side of that, we're going to have an isotonic solution, which is then going to dialyze the solution. The reason we use an isotonic solution, it's going to be isotonic to all the salts that are in your blood. Otherwise, you'd have all the salts removed too. Okay? What it won't have, though, is the specific molecules that we're removing as waste. And so those specific molecules are then going to diffuse across that semi-permeable membrane. Okay? And so the concentration of your waste molecules lowers in your blood, increases in the dialysis solution, right? And that dialysis solution gets cycled away into a storage or it gets purified. Okay? Some of these machines are actually pretty advanced and have like filters that then purify it and can recycle the solution. Okay? This is actually a place where there's been a lot of development. Interestingly enough, you know those machines that mix soda to whatever type of soda you want? Okay, that guy also invented Segways and the medicine delivery systems for babies. Kind of an interesting guy. And this is the sort of thing he got lots of patents on, is the sort of dialysis, very, very specific, like pumping systems. Okay. So the urea is one of the major components. This is actually the component in your urine that has that smell. Okay. The urine smell, literally the name urine urea, right? Okay. So the small molecules, waste molecules, are going to diffuse out of the passing blood into the dialyzing solution. The dialyzed blood is going to return to the patient. This right here is the dialysis process with a cartoon in place of the actual machine, because it's actually kind of difficult. Well, they don't usually make the machine so you can see inside of it. It's actually not that difficult to make these machines visible inside of them. And I've actually seen them before where they are visible inside. But they don't typically do that. So this right here is going to be your blood pumped off. You have a pump to make sure it moves. Does anybody know if you want to create vacuum or if you want to put positive pressure into a pumping system? So you always want to pump on the thick side of things, okay? You want to create what's called positive pressure into a pumping system. And so this is why they put the pump right here where it's the blood side, because this is going to be the most concentrated side of this. And we'll put positive pressure in this. What happens if you put negative pressure is the tubes can actually collapse a bit. And it's going to limit your system. And if you put it on a vacuum, it'll just collapse to completely and nothing happens. Okay? Causes a lot of problems. Okay, so this right here is your dialyzing solution. Notice we just wrap the tube up in that dialyzing solution. We have lots of surface area here. And so we can get lots of diffusion happening, right? And then we bring that back over to the person and bring it back into their system. Okay? Anybody have any questions about that so far? Okay, fantastic. Okay, let's talk about the transportation across cell membranes. So cell membranes are semi-permeable. Everybody got that okay? That's a separate thing than what we're going to be talking about now. Okay? So cell membranes themselves allow some things to come through. And that's simple diffusion, and that's the passive part right here, okay? And this is things like water is a very common one, and that's neutral. It's very small, so it can just fit through the cell membrane, the little gaps between the fatty acids, okay? Doesn't need a specific channel. It doesn't need anything like that, okay? Okay, so the other one is going to be integral membrane proteins. And so one of them is going to be facilitated transport. So what we'll have here is we'll have a protein. It has a hole in it, okay? This hole oftentimes has things like hydrogen bonding that happen inside with what it transports. So, but the important part of this is facilitated transport does not use up energy to happen. It's still driven by diffusion. And so that's overall what's going to drive this force, okay? The difference between this passive simple diffusion and a facilitated transport is that these are things that won't be able to go through the cell membrane, okay? Big one is any salt. So for example, magnesium, sodium, they can't go directly through the cell membrane. They're charged, okay? They can't go through the non-polar environment, which is the cell membrane, right? So for all of those, you actually need a facilitated transport of some sort, even if you have a higher concentration on one side than the other, okay? And that higher concentration on this side will still drive the facilitated transport, but you need some sort of gap that can bring this through the cell membrane. Okay, so this one right here is going to be an active transport. What happens in an active transport is you have a ATP energy being provided that's going to power this like a pump would, okay? So typically what these are is they'll bind something, you'll bind the ATP, and then it will shift and push it through, okay? And that's going to provide the energy, and you'll build up a concentration on the other side. So this is going to be coupled with something that will use energy, provide energy to push a concentration gradient the reverse direction of what you would normally. Okay? Okay, anybody have any questions about that so far? Do you understand why the active transport? Because you actively have to provide energy to transport it, right? Okay, very good. Okay, so these are some of the small molecules that can just be passively transported through the cell membrane. They don't require any special channels, nothing. O2, N2, and CO2. These can all be directly diffused through the cell membrane. They're small neutral molecules. They fit just fine. Okay. CO2 is actually incredibly, O2 and CO2 are incredibly important ones of those, by the way, because that's actually how you breathe, right? So, for example, those are the things you breathe in, and then your cells need to gather, and then your cells have to put that in the blood system and remove, right? So again, diffusion is going to move solutes to equalize the concentrations on either side of your membrane. And so what you'll see is the immediate environment is going to have a slightly higher concentration, and that's going to then push those through diffusion, right? Okay. So again, that process does not require any additional energy. That's going to be referred to as passive diffusion because you're not actually really doing anything. They're just going through your cell membranes. Okay. Other nonpolar molecules like steroids can also passively diffuse through cell membranes. This is one of the reasons why they're nonpolar. Is them being nonpolar allows them to diffuse across the cell membrane because they can associate with the nonpolar fatty acid tails, right? Okay, so if we want small molecules and ions to pass through the cell membrane, they don't passively diffuse through the cell membrane. So what we have to have is polar channels that will open and close. This is going to allow things like small polar molecules and ions to be transferred across the cell membrane. These proteins are going to often be integral membrane proteins. They're going to span the phospholipid bilayer, and so they will actually be little channels that are made to span the lipid bilayer. This is going to be facilitated transport, doesn't require energy. It's still going to be a concentration gradient driven process. You just have channels to facilitate it. Okay. The glucose transporter proteins are going to be found in virtually all cell membranes and facilitate transport of the glucose in the cell when the blood glucose concentrations are high. And remember, these are not going to be able to go through the cell membranes because glucose is going to be too big and too polar to actually go through the fatty acid tails being associated together. So if we're talking about transporting ions or small polar molecules across the cell membrane in a direction opposite to equalizing concentrations, we're going to actually have to put some power behind it because this is not going to be spontaneous. And so this is where your active transport comes in. We're going to push a concentration gradient against osmosis or against diffusion, right? Excuse me. Grab my water real quick. Okay. So again, active transport is going to require energy. It doesn't have to be ATP. It can be other forms of energy. There's several different forms that will work. But ATP is the most common form by a pretty long shot. Okay. One active transport pump is actually the K plus, potassium plus, H plus. So we exchange K plus with H plus. And this is an ATPase. It's actually going to control the concentration of potassium hydrogen atoms in your stomach. And so it's how you build up a concentration of acid in your stomach. Okay. Or actually modulate that concentration for that matter. So normally you would have a concentration of acid in your stomach, but it needs to stay in a certain range. Okay. So medications like Zantac or Pepcid actually block the production of stomach acid through these pumps. That's what they work on. Okay. And these require ATP, that's where the ATPase comes from, to drive that process of potassium and hydrogen exchange. Okay. You may be wondering why potassium and hydrogen are being exchanged. Well, that's to make them more or less isotonic with each other, right? So we're exchanging cations. So you don't have all your water from your body rush into your stomach and fill it up, right? You realize that if you concentrated just positive, like you just concentrated charge in your stomach, it would make it hypertonic, right? It'd be like drinking seawater. Okay, this is the study guide for the chapter. Oh my goodness, we're actually making really great time, aren't we? Okay, so that right there is the material for chapter 8. You can feel free to apply, go ahead and print the study guide if you ever want, and check the items off to make sure you understand the different materials. Anybody have any questions about chapter 8? No? Okay, fantastic. Excellent.